Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, my name is Jonathan Goldstein, and I would like to introduce Milos Nikolic, who is visiting us from EPFL in Switzerland. He is going to be talking to us about high-performance incremental query processing. He was an intern here last summer, so without further ado, I'd like to introduce Milos.
Thank you, Jonathan. Okay, before we start, I'd like just to say a few words about me. I'm a sixth-year PhD student in the data lab at TPFL, working under... It's on. It is on.
Oh, it is on? Oh, it is on.
Okay. Yeah, so I'm a sixth-year PhD student at TPFL. I work in the data lab under the supervision of Christoph Koch. And as Jonathan already said, I spent my last summer here working some exciting stuff on adding support for DSP operations in Trill. And yeah, I would like to thank this Jonathan and Dries for a great summer that I had. And I would also like to thank you for this opportunity to present you my work. So my research field is, my research focus is mostly on data, is broadly on data management systems, more specifically on stream processing and incremental computation. And today I'm going to talk about how to build efficient incremental query processing engines for complex analytical queries. So the world is increasingly going digital with data being generated from many different sources. For example, sensor networks in the context of the Internet of Things, or social networks, web platforms, or mobile devices. And with such massive amounts of data being generated online, it is of increasingly importance for companies to react quickly to events that can affect their business decisions. So many of today's real-time applications require real-time and online analytics of a large and dynamic data sets. For instance, web analytics for examples like web analytics or sensor network or high-performance algorithmic trading or cloud monitoring are all instances of applications that require some sort of real-time analysis. And the important for these applications is that they monitor some sort of the state of the underlying data. And this state is usually defined as views or aggregate representations of the underlying data. So on a very high level, the general model of these applications can be described as follows. As inputs to these systems, they receive a stream of continuously arriving data. This could be stock feed updates, or this could be sensor readings, or user clicks on the web. These events are processed by a runtime engine that continuously evaluates certain views over this data and produces results for the decision support system, which takes corresponding actions. For these applications, the data changes at very high rates, so it is of crucial importance for users to be able to have frequently fresh views of the data in order to be able to promptly react to certain conditions. So it is of the key importance for these runtime engines to provide answers in a timely manner with low latency. Additional requirement is that users should be able to express complex analytical queries in order to discover insights from the data using complex analysis. And finally, big data applications require scalable processing in order to handle in order to speed up query evaluation or to handle growing memory requirements. So what of the existing systems we can use to build such runtime engines? When we talk about streams of data, the first thing that comes to our mind is stream processing systems. So typically, classical stream processing systems process a stream of events using continuous queries over windows of data, where windows is just a sequence of events. As the windows advanced over the input stream, the engine recomputes the result for each window. Now, the stream processing engines typically provide low latency processing of data. However, they often lack the support for expressing complex analytical queries. For instance, queries that can handle nested aggregates. But in addition, since these engines work with overlapping data sets of data, they're often based on the notion of incremental processing. So the idea of incremental processing is the following. We're given a database and a stored materialized representation of some computation. Now, when the database changes, our goal is to update the final result. However, we don't want to recompute everything from scratch because that might be costly. Instead, what we would like to do is to derive a so-called delta computation, which is usually structurally simpler and works with less data, and allows us to express what has to be changed in the output given the current state of the database and an incoming update. Now, the idea of incremental processing has been successfully applied in many commercial database systems in the form of incremental view maintenance. Here, for a given materialized view defined as a SQL query over a set of base relations, the systems derive delta queries for updates to each base relations and execute those delta queries upon every change of the database. And the execution of these delta queries is done using the classical query execution engine. So both stream processing systems and database systems have some sort of incremental processing in it. So let's see how well they perform in practice. So we run a benchmark here where we compare a commercial database system and a commercial stream processing system. We compare on a set of TPC-H queries, where the TPC-H benchmark is a well-known benchmark for evaluating database systems. And on the x-axis, we evaluate a set of TPC-H queries, ranging from those queries that have, from flat queries that have only multi-way joins, all the way to some queries that have nested aggregates in it. What we measure here is the single-tuple performance, meaning that after insertions or each insertion or deletion into the base relation, we're doing our best at maintaining the result fresh. Right, so we have stream of events that are, so in this case, the stream of events is generated from a TPC-H database and consists of interleaved insertions and deletions. So the performance for these systems is not so great. So both database system and the stream processing engine can process roughly up to 100 events per second. That means after each event, we want to maintain the fresh result. Are these numbers good enough for real-time applications? Well, one can say probably not, because we are seeing much more velocity in the data nowadays. So in this talk, in the first part of this talk, I'm going to present a system that's called DBToaster, which combines incremental processing with code generation to produce efficient, lightweight stream processing engines that are tailored for the given query workload. And as you can see from this performance graph, DBToaster can achieve up to 5 orders of magnitude better performance than this commercial database and stream processing systems.
So can you give some intuition why it's only 10 to 100 tuples per second? Why is it that it's not?
Yeah. Sure. For database systems, basically, well, they're not meant for this kind of workloads where you have frequent insertions and deletions and you want to maintain some of the result. And in fact, in many cases, incremental view maintenance in database systems was often slower than the complete reevaluation, right? Because of all sorts of overheads that are coming from components that are not involved in query processing, like concurrency control, transaction management, buffer management, things like that. For stream processing engine, the one that we used in our benchmark, basically we were not able to exploit the internal mechanisms of this stream processing engine because they were tied to the window semantics that they're meant for this kind of application. But here we have a long-lived data, right, where data cannot be captured by a single window. So what we had to do instead is to internally maintain in-memory tables and then do incremental evaluation as much as we could, right?
So how big a system were you running this test on? These tests on? What was this is?
So this was a single node experiment. The test data was not that big. It was actually a stream of insertions and deletions, which is synthesized from a 1 gigabyte TPC-H database. And in many cases, like those DBX and stream processor were not able to process the whole stream within a 1 hour time limit.
So I was more asking about what the hardware platform was. Were you using a multi-core NUMA machine?
For DBToaster, it's single core execution, single-threaded, single core. For database systems, it was a multi-core thing, but I'm not sure that it was using something, right? So this for DBToaster, it's for sure single-threaded, single node performance. Okay. So the goal of my PhD thesis was how to build efficient incremental processing engines for complex analytical queries. And in this talk, I'm going to focus on 2 types of analytical queries. First, I'm going to talk about traditional SQL analytics, which are very much used in OLAP systems. And this analytics typically involve aggregates over multiple dimensions of the underlying data, or might involve queries with nested aggregates. In the second part of this talk, I'm going to talk about a more complex analytics, which can be expressed as linear algebra programs. And this analytics allows us to actually discover some insights from the database using algorithms and models from machine learning, scientific computing, or data mining. So I will start with talking about how to incrementalize SQL queries. So DBToaster is a compiler for database queries. It takes as an input a SQL query and produces a lightweight engine, stream processing engine, that can that efficiently maintains the query result upon every change of the database. The compiler consists of 2 parts. The front-end part transforms SQL queries into maintenance programs, where each maintenance program consists of trigger functions describing what needs to be done in the database on every update of the base relations. Yes?
So what class of queries can you handle?
For incremental view maintenance, so for efficient, all flat queries, and also nested queries, where the outer query has an equality correlation with the nested query, right? That we can handle efficiently. In all other cases, we can fall back to reevaluation, right? And the DBToaster in its whole can support the full, well, almost the full SQL. We don't support nulls. We don't support order by sorting, but everything else should be in there.
So, for instance, you showed query 21, right? That has a subquery with a disjunction, right? Like not exists subquery.
Yeah.
So you can handle that? Can you create a materialized view that can handle that?
Yeah. Not exist? Yeah, we can handle. I might defer the question to how to handle this nested aggregates to the Q&A session, because it's a bit technical, but yeah, we can do that.
Those things you cannot handle, how many of them are intrinsic to your approach? Like it seems like nulls you could probably add, you just didn't
Yes,
bother with
nulls
sorting.
does require some engineering effort. Sorting online, well, that's going to be costly, right? What we can, of course, there is one more thing. We cannot handle min and max efficiently. For the moment, we are rewriting those as nested queries. Like there is no such element that is greater than this. But in general, for this case, min and max, we would have to maintain basically the whole base relation, right? And then incrementally maintain. There might be several special cases if you just have insertions, but it's not that interesting, right? Okay, so the front-end part is the one that transforms SQL queries into maintenance triggers, and the back-end part takes those maintenance triggers and generates native code, right? For the moment, we support C++ and Scala code generation for single node execution and Spark for distributed execution. Okay, this generated code is self-contained, right? It doesn't require any database sitting behind it, right? It can be easily embedded into this kind of real-time applications, right? Because we're just producing a source code that consists of trigger functions. Or it can be used in other cases up to the user convenience. So how do we go from these queries to maintenance programs using classical incremental view maintenance? Well, typically we have the following 3 steps. We're given a query, and the first thing we want to do is we want to store to materialize the result of that query. Then we can derive delta queries for updates to base relations. Once we have those delta queries, we can optimize them. And once we optimize them, we can produce trigger programs. And everything is done at compile time. Now,
one question, do you do this tuple at a time, or do you batch?
We can do both. And I'll have some discussion about the trade-offs. So this is a classical incremental view maintenance. Now, the problem is these delta queries, although they are simpler, and usually, for example, for single tuple updates, they have one join less, right? And work with less data. However, they're not free. You still need to execute them, right? If you have an n-way join, a delta query still needs to join together n-1 relations. So the key inside of DBToaster is to repeat this procedure recursively. Now, once we have these delta queries, we can materialize the update independent part of each delta query and then perform incremental view maintenance for that delta query, creating higher order delta functions, right? And with each derivation step, these delta queries will become simpler and simpler until we reach until we get a delta that doesn't depend on the database system, on the database anymore, right? And whose delta is 0. At that point, we can stop. So the overall idea of this recursive approach is to create a hierarchy of these materialized views that are going to maintain each other, right? And at first, it might appear counterintuitive that, OK, we are storing more data. How is that going to help us to achieve better view maintenance, right? But the key insight is these additional auxiliary views are actually helping us to significantly simplify the maintenance job that we have to do for each of these queries. So how do we do that? We start from the top, where we have our query, and then for each base relation, we compute first-order deltas. And then for each delta, we materialize the update-independent part of it. And then for each materialized delta query, we're going to compute the second-order delta for each base relations. And we continue with this procedure recursively until we reach the 0 deltas at the end. Now, we can use these deltas to update, to maintain the views of the parent, to maintain parent views, right? So the second-order delta might maintain the first-order delta, which might maintain the final query. So that way, we created a DAG of dependencies between those materialized views. And all of these materialized views are self-maintainable, meaning that there is no need for some additional database system that will help us to maintain these queries. So let's see how this compilation procedure works on a simple example. So here we have a two-way simple query which joins together two relations, R and S, and has an aggregate on top of that. So in this particular case, what we want to produce are two trigger functions that will tell us what we need to do how are we going to maintain the final result upon every insertions or into one of these base relations. For the moment, we are going just to consider the insertions, but we can also similarly construct trigger programs for deletions or for arbitrary updates. So let's see how we're going to do that. The result of this delta query is just a single value. So we're going to materialize this single value using variable q. That's the first step of our procedure. And then we consider one new update to the relation S. The new result for this query is exactly the old query where the relation R is replaced by a union of R and delta R. I'm slightly using the SQL notation here, but hopefully you will get you understand the point. However, we don't want to re-evaluate this query from scratch. We would like to derive a delta query that will help us to reuse the previous result. In this case, the delta query is pretty much simpler. It's the original query where R is replaced by delta R. Now we're going to use this delta query to incrementally update the final result. Now, since this input change is very simple, we can actually exploit this simplicity to replace these variables A and B that come from delta R with the actual constants delta A and delta B. Once we do that, we don't have the join inside this delta query. Now, since delta A doesn't depend on the S, we can use the distributivity of addition to pull out this constant in front of this delta query. What we have here now is a delta query that depends only on the relation S, but it has this input variable delta B, which we are going to get rid of by rewriting this query using group by and following by a lookup into this materialized result. And now we reached the end of the first cycle where we are going to recursively repeat this procedure. We have this delta query, which depends only on S, right? And we're going to materialize that. Since it's a group by query, we're going to use something like a hash map for storing the materialized content of this.
So if S.B is a key, won't you be materializing a lot of data that's linear in the table size? If you're doing a join on the keys, for instance,
yes,
then this group by would be as big as the table size.
Yes.
So you would still materialize it, or you have some
sure.
costs?
Yeah.
Okay.
And we'll see why, right? Once we materialize this, now we can suppose we have this materialized result, we can rewrite the delta query as a simple lookup operation into this materialized view, materialized map, followed by multiplication. That is our delta query that we are going to use to update the final result. However, this new view that we just materialized needs to be maintained, right? So on every update to S, we need to compute the delta query for this materialized view. And in this case, the delta query, because we are considering only single-tuple updates, is just a simple constant delta C, which is going to update only one element of the materialized view. Okay, now we created one additional materialized view, and we created some statements in our trigger programs. Now we can proceed again by considering from the top level query and considering updates to relation S. If we do that, we are going to, in a similar way, materialize one additional relation over one additional view over relation R, and add two new update statements. And that's it. That's the whole compilation procedure. And these are the trigger programs that we are generating. Notice the following. We materialize 2 additional views, right? But these views are not the whole base relations. These are group bys over certain columns that are used in that query, right? So we project away all unused columns and aggregate over the ones that are used. So in case of if B is a primary key, right? We won't reduce the number of tuples, but we're going to project away the A column, right? Because we don't need for this maintenance. So the important thing about this generated programs is that these triggers run in constant time. In this particular example, if we have updates to relation R or S, we just need to perform a constant amount of work in order to update the result Q and all other materialized views. So in general, our trigger programs might not have a constant running time, but in many other cases, they provide some benefits that cannot be achieved with other incremental view maintenance techniques. For example, a classical incremental view maintenance technique cannot incrementally maintain the result of this query in constant amount of work. OK, once we have this trigger programs, the second phase of our compiler is the actual code generation phase. And here we're going to use specialized data structures for storing the contents of these materialized views. In our case, we are going, since these maps represent group by queries, we're going to use a hash map with memory pooled records for storing the contents of these 2 additional views. And we're going to specialize the final result, the type of the final result, to be a primitive type. Now, for generating the actual trigger programs, we just need to transform these maintenance statements into the actual code. In this particular case, it might seem straightforward because they're very simple. But in general, they might involve also some joint processing in the actual code generation. OK, so how does it perform in practice? Well, this is the graph that we already seen, except that we have another column here, which is just DBToaster with the classical incremental view maintenance. So basically, with that additional figure, we want to measure the impact of our recursive incremental compilation algorithm. So as you can see, just by using DBToaster and code generation, we can get 1 to 2 orders of magnitude better performance than existing commercial database systems. But then if we just use this recursive incremental view maintenance approach, we can get up to 5 orders of magnitude better performance on average than these systems. OK, so yeah.
There's a space versus time trade-off here, right? So what is the amount of space required? Are you also doing that?
So the memory overhead of using DBToaster, obviously it has some memory overhead, right? It pretty much depends on the query that you're targeting. But if we, let's say, consider the typical star schema query, all the materialized views will not have more tuples than the fact table. That's for one. And in practice, they will usually have much fewer tuples. Why? Because we are going to include static conditions for a given query whenever it's possible to filter out tuples that don't match static conditions. That's one. The other thing is we are going to project away columns that are not used for that particular query workload. So we don't need to store the whole materialized relation, the whole base relation. And the third one, we are going to aggregate over those these materialized views are aggregate representations of the base tables. So if we aggregate over some columns with very small domain, right, that might have very small memory footprint. But in the case of let's say, TPC-H queries, it's usually much lower than the size of the base relations.
A couple of questions. So one is on sort of the idea, your idea that you can materialize additional views with the sole purpose of speeding up incremental maintenance of an algorithm, right? This is sort of one idea that you have. And if you, did I misunderstand your idea?
No.
Right. So about 20 years ago, there was a series of work done by Inderpal Singh Mumik and others, which essentially pursued the same idea.
Mm-hmm.
So can you comment at a high level what are the significant differences?
Sure. So the problem of view selections and using these views to answer some other queries, right? It's nothing new it's nothing something that is invented by DBToaster, right? It has been before. What's novel in DBToaster is this recursive incremental view maintenance, where we have a way of transforming one query into delta queries, into a hierarchy of delta queries which maintain each other results, right? Yes, that might be also possible to achieve before that, right? But there is also a nice theoretical result, which was not done by me, right? Which tells if you use this recursive incremental view maintenance technique, then for every materialized view that you have in your system, you just, for every value inside, you just need to perform a constant amount of work to update that value. So that means that this hierarchy of materialized views is essentially embarrassingly parallel, right? Whether you can exploit that in practice, that's another question, right? But it's a nice theoretical result that separates classical incremental view maintenance from recursive incremental maintenance.
My second question was this speed up that you get, can you sort of break it down by saying how much you get from the code gen optimization versus
so that's the DBToaster with IVM, so DBT IVM. That's just code generation with classical incremental view maintenance. And DBToaster is code generation with recursive incremental view maintenance. So as you can see from this graph, using code generation and classical incremental view maintenance, you can get 1 to 2 orders of magnitude better performance. But the real benefit comes from using this recursive incremental approach, where you can get up to 5.
Why you pick these 6 TPC-H queries, and can you support outer joins?
So can we use outer joins? We don't support nulls for the moment. So we actually had to change some of these queries to replace outer joins with inner joins, and to avoid and to remove order by clauses, right? Because we don't support sorting.
So what about dot K? Is that a problem?
It is a problem, because you would have to maintain the whole. It's like min and max. You would have to maintain the whole history of these base values, right? Which we don't support for the moment.
So how many TPC-H queries you can support?
We have the full TPC-H benchmark, although we modified some of the queries, right, to avoid these restrictions that we don't support. So we have results for TPC-H and also for some TPC-DC DS queries. Yeah.
So do you have a graph for the memory utilization for these systems?
No, I don't have a slide. We have it in the paper.
How does it look like?
Well, depends on the query, right? For some queries, it can stabilize because you materialize the view and you have seen all distinct values from your keys, right? So whatever you aggregate on top of that, it won't increase your memory consumption. But there are queries for which, as you keep seeing new data, right, new keys, new primary keys, the memory consumption will grow, right? But that's the same case as with other systems. So the relative ratio, I would say that for this kind of workloads, is that the size of these materialized views is usually much smaller than the size of these base relations. Just because we project away columns, we just keep only the minimum amount of data that we need to maintain those queries. Okay, so yeah, one can say, well, this is for single tuple processing. What about batch processing, right? Database systems are much better for doing that. So we did an experiment where we use a commercial database systems, and we vary the size of the batch, in the size of the input batch that we are processing, and we compare incremental view maintenance and review relation. We can see that as we increase the batch size, obviously as expected, the number of processing tuples per second will also go up. However, even for very large batch sizes, these performance numbers are still around 300x slower than DBToaster with single tuple processing for this particular query, right? Other queries might differ, but still there is at least 1 or 2 orders of magnitude better performance with DBToaster. Now, the question is, can we use deep batching inside DBToaster and get similar performance improvements? Well, the answer is yes and no. So there is traditional belief that batching will always improve performance, right? And that's true because it might give you better cache locality. It might also amortize invocation cost of these trigger functions. And batching is also crucial for distributed execution because we want to amortize the network communication costs. So how do we support batching, or how do we do batch processing inside DBToaster? So we are, again, considering the same query, right? Simple two-way join with an aggregate on top. For that delta query, we're going to materialize the result in a variable Q, and then we're going to derive query for updates to relation R. Right? The delta query is simple enough. We just replace R with delta R. Then we can do some traditional query processing optimizations, like pushing the aggregation down the expression tree in order to minimize the amount of data that we need to join. And in this case, we can exploit the distributivity of this sum operation to push the sum down the expression tree and compute aggregates of delta R and S. And if you notice, the right operand of this join tree is exactly the materialized view that we also had for single tuple execution. So we're going to materialize this query, and we're going to repeat the same procedure for updates to another relation, S. And in this procedure, we're going to materialize an aggregate over the relation R. And now we have materialized two additional maps, like before, right? That one of them is over S, one of them is over R, and the final result Q. So on trigger update for R, we need to maintain Q and MR. The delta query for this MR is a simple aggregate over the delta R input batch. And if you notice, that is exactly the same expression that is used for maintaining Q. So we can exploit some commonalities between those delta expressions to actually reduce some computation and evaluate these delta expressions efficiently. So in general, for this query, if we were if you are going to write a trigger program for this query, it will consist of 3 steps. First, we're going to pre-aggregate the input batch that we are going to get. Second, we're going to use that batch to compute the delta Q. And finally, we're going to use the pre-aggregated batch to update the materialized relation. These are 3 basic steps. You don't need to understand them. But the main point here is that we can pre-aggregate input batch, exploit the fact that we have a collection of tuples. We can try to reduce their size as a first step, and then use this aggregated representation in the further computation of our delta programs. Now, how are we going to translate this program into C? Well, for pre-aggregation, we have to use intermediate collections, right? That would involve looping over the input batch and aggregating results. For updating Q, we're going to evaluate this join as an in-memory hash join, where again, we're going to loop over this aggregated representation of batch. And for updating R, it's just looping over this pre-aggregated batch and updating the final result. Again, there is no need to understand this code, but this is what a trigger program would look like in C if you were to compile this, this input query. Now compare this batch version versus the single-tuple version, right? Obviously, there is the single-tuple version is relatively simple, right? Because it's just of 2 statements, where this batch version has much more performs much more computation for the given input size. Notice several differences here. First, the single-tuple version has specialized primitive type trigger parameters, whereas in the batch case, we have a generic list of tuples. That is actually a powerful optimization that can allow us to, that allows the C++ compiler to treat this delta A and delta B as constants and move them out of loops during this compilation to native, to machine code. Second of all, the single-tuple version doesn't have any intermediate results, right? We can eliminate those loops as well because we know that the input batch size is of size 1. And we can also do partial evaluation, inlining, and things like that, right? So if we were to specialize this code, we will get this single-tuple code. Now the question is, which one is going to perform better, right? The single-tuple code obviously has better cache locality, instruction cache locality, right? Because it's much smaller. The batch version might have better data locality because it's going to iterate over this collections of data, right, in a tight loops. And batch version can also profit from this pre-aggregation, from this first step, because in this step we can, in some queries, we might reduce the domain to relatively few values and then make the subsequent computation very cheap. So we did an experiment comparing the single-tuple performance with batching performance for the full TPC-H benchmark, all 22 queries. So what we did here is we measured the performance of single-tuple processing, and we measured the performance of batch processing for different batch sizes. We varied batch sizes from 1 to 100,000. And for each query, we picked the best batch size and the best throughput numbers that we get, right? And then we normalized those numbers by the single-tuple performance. That's what is shown on the x-axis. And the y-axis shows the cumulative count for these queries. So let me explain this curve. So what we have here, what we can see from these graphs is that for 5 queries, the relative ratio of this throughput is less than 1. That means that single-tuple processing is better than any batch processing for any batch size. For
batch size 1, because you have a
for batch,
more complex.
Yeah, for batch size 1, it's always better, right? Yeah. But even if you increase the batch size, this pre-aggregation step doesn't help you that much. You might be pre-aggregating over primary keys, so you won't reduce the size of the input batch, and you won't see any benefit. In fact, you will see worse performance. For like half of our workload, we can see that single-tuple performance is maybe 20% worse than, at most 20% worse than batch processing. For 14 queries, it's like 50%. But notice also that for this best batch throughput, for different queries, this might be different batch sizes. So if we had just one batch size, these numbers might be even worse, and it might be even better in favor of single-tuple processing. However, there are certain queries where batch processing can actually deliver very great performance. And in like 4 or 5 queries, we have seen improvements up to 4,000x. And this is mostly because of batch pre-aggregation, which allows us to reduce the domain to very few elements such that subsequent maintenance statements are relatively cheap. Okay, what about distributed execution? Well, the goal of this part is to transform these local incremental programs into distributed programs that can run on large-scale processing platforms. And we do that for two reasons. We want to speed up query evaluation or maintenance, or the maintenance work, and we want to accommodate more data. Now, one crucial difference between this work and classical distributed query optimization is that we're trying to optimize, we're trying to distribute these incremental programs. These programs consist of triggers, and each trigger consists of statements. And these statements, they have data flow dependencies like in any other program, right? For example, the delta in the first statement might be using views that are maintained in the second statement or in the sixth statement. That means we cannot arbitrarily reorder them, right? So we have to be careful about how we're going to interleave the execution of these statements in a distributed environment. So that is the reason. So our first attempt was actually to execute this trigger programs on a synchronous, on a distributed system with a synchronous execution model. And that turned out to be quite bad because of this synchronization overheads that we had to introduce, or some compensation that we had to introduce for dealing with this, for ensuring the consistency of these programs. So our approach is to distribute these incremental programs using processing platforms with synchronous execution models. For example, to execute these programs on top of Spark or Hadoop, right? So we assume that we have one master node with a bunch of workers, and we execute this, we represent this computation as a sequence of jobs. Now, in order to achieve this distributed executions, we had to change our language and introduce some location tags or to mark each expression with some information about where it is located in a distributed environment. So each expression has can have one of three possible values. For instance, it can be marked as local, meaning that the expression is executed and the result is stored on the master node. Can be distributed by key, meaning that the whole materialized view is partitioned across all workers by a certain key, or it can be distributed randomly, which is usually the case with input batches. And we also introduced some communication primitives in order to achieve this distributed execution. And these are very well-known communication primitives that allows us to, for example, repartition one distributed collection, or transform one distributed into one local collection, or distributed a local collection across many workers. So the way we do that, we start with a local statement, single statement, and for each materialized view in this graph, we are going to annotate to say where the location of this result is. We assume that such information is provided from the outside. It doesn't matter in our case. So let's say that delta R, the input batch, is randomly partitioned across all workers, that the materialized view MS is partitioned across by column B, and the final result is stored on a local node. So how do we build these distributed statements? Well, we traverse this tree in a bottom-up fashion and try to introduce communication primitives where they are necessary in order to preserve the semantics of these query operations. For instance, since we have to compute a join between those two relations, they have to be partitioned on the same join key. So that means that we have to repartition one of the input batches. And once they are partitioned by the same key, we can perform local join operations, followed by local aggregations, and then finally we can introduce one gather primitive to collect the result on the master node. So that way we can execute one local statement as a sequence of stages And these stages can be either distributed stages, like happening in parallel on every worker, or they can be local stages, which are happening only on the master node. We also have some communication stages where we need to send data around and in order to ensure correct semantics of query execution. Now that is how we transfer one statement. So these programs have multiple statements, and we can simply concatenate those statements and say, okay, this is your distributed program. You can, from here, you can see it is relatively straightforward to generate some code that will run on top of Spark. However, this code is going to be very inefficient because it requires a lot of communication. So what we do in this stage, we try to reorder this. What we do in this phase, we try to reorder these stages and merge those stages that can be merged, that are compatible. For example, we can merge distributed stages, or we can merge local stages. And while reordering this, we try to preserve the statement dependencies that exist in the input program. Once we have that optimized distributed programs, we can generate code for any system that has a synchronous execution model. In our case, we generate Spark code. So we did some experiments. In this case, we have a stream of 500 gigabytes synthesized from a 500 gigabyte TPC-H database. And the batch size is fixed to 200 million. And what we measure here, we compare the time it takes to process one batch with respect to different number of workers. And we have several queries here, starting from a very simple one, like query 6, which just requires a local pre-aggregation and one collection phase on the master node. And as you can see with our implementation on top of Spark, we can go around as low as 0.5 seconds for processing this 200 million tuples using, I think, 800 nodes. For other queries, like query 3 and query 17, they require 2 communication stages. So, and they also require a certain amount of data to be transferred. So in those 2 examples, right, performance is much higher. So the latency is a bit higher, around 4 seconds. And this is mostly comes from the overhead of the underlying execution engine, in this case Spark, right? Since we have to execute several jobs in order to maintain this query, the internal overheads of Spark are actually causing this latency. And for some queries, like query 7, where we have more than 2 communication stages, and in those communication stages we shuffle a lot of data, right? The performance really suffers, and it's around 32 seconds, flattens out with 200 nodes. And basically this is something that we cannot improve using Spark, because mostly the latency is affected by the garbage collection that is happening on this workload nodes. And we don't have a way to actually change that. So building a specialized system for this kind of workloads would really help us here. OK, with that, I would like to conclude this first part of the talk, and I'll try to jump to the second part. So in the second part, we're going to talk about incremental incremental processing of machine learning of linear algebra programs. So many existing machine learning algorithms can be described as iterative linear algebra programs. For instance, if you take the order and least square method, which is a common way to fit a curve to data, it can be expressed as a sequence of operations over matrices. Now, in this case, the operations involve classical matrix multiplication, inversion, and transpose. Now, the problem with this analytics is that they have to work with increasingly larger data sets, which is becoming expensive. And these data sets are changing, usually through small changes compared to the overall data set size. So we built a system called LINVIEW that performs incremental processing of iterative linear algebra programs. As input to this system, we take APL-style programs like MATLAB programs or Octave programs, and we transform them into incremental engines that efficiently maintain the query result. Now, as input to this system, we consider a language consisting of standard matrix operations like multiplication, addition, transpose, matrix inversion. And this language is sufficient enough to express many of the machine learning algorithms. So let's see what it means to perform incremental processing in the context of linear algebra. So here we have an example of matrix-powered computation, where we want to compute the fourth power of a given matrix A, which is a very common task in many real-time applications. For instance, like in graph processing to compute reachability between nodes, or in PageRank computation. So we want to express this computation as a sequence of two statements. And in these statements, they involve full matrix-matrix multiplication. In all these cases, I will consider dense matrices, right? And the complexity of these matrix multiplications, with some simplification, it's n to the cube. Now, when the input matrix changes, let's say one element just changes, we can recompute everything from scratch, but that might be costly, right? Especially if the updates are small. What we want to do instead is to derive this incremental program, which is hopefully simpler enough, and it will tell us how to compute only the delta change in the result more efficiently. Now, the LINVIEW approach is beneficial for linear algebra programs that involve matrix operations. In other words, the complexity of the original program has to be n to the cube. And for those kinds of programs, we're going to generate incremental programs that will exploit the sparsity of this input to achieve better asymptotic behavior. Now, the question is, how are we going to derive these incremental programs? How are we going to evaluate these delta expressions? And how are we going to represent them? Now, for delta derivation, we're going to rely on the basic properties of matrix operations. For instance, if you want to incrementalize this matrix multiplication, we'll just say that we're going to rely on the distributivity of matrix operation with respect to addition to derive a delta B, which consists of a sum of 3 terms. Right? This is relatively straightforward. Now, how are we going to evaluate those deltas? Suppose that the input delta consists of a single entry change. Now, in order to compute delta B, we're going to evaluate this sum of 3 expressions. And the final output will contain changes in one row and one column. With these blue markers, I'm going to denote entries that might be potentially non-zero entries in delta matrices. So we can see that for a single entry change in the input matrix, the result, the delta B, has potentially changes in one row and one column. Now, if we're going to push this delta to the second computation that computes the delta C, we can see that the whole output is going to be changed. Well, that causes a problem because, well, it tells us the following. The first, that incremental evaluation has a lower bound of n squared, so we have to change all the elements, so we cannot go below that. The second thing is, if we want to use this delta C in subsequent delta evaluations, we are going to end up doing full matrix-matrix multiplications. So very quickly, in just 2 iteration steps, incremental evaluation will lose its benefit over re-evaluation. And we call this the avalanche effect. A single local change has exploded in just 2 steps and contaminated the whole output. Now, how are we going to deal with this? Well, we just seen that if we represent deltas as single matrices, it's not going to work. Now, the main insight of our work is that although these delta matrices might have non-zero elements everywhere, they often have a simple structure, meaning that they can be decomposed and written as a product of 2 matrices, 2 small matrices, and that have low ranks. For instance, if we take this input, delta input, which has only one element changed, we can compress and represent the same change as a vector outer product, as a product of two vectors. And I'm going to argue that this factored representation of these deltas can help us to achieve efficient evaluation. Let's see how we can do that. Suppose that delta A is a given input change and is an outer product of two vectors. It's called rank 1 update. And now when we want to compute delta B, which we do in the same way as before, now we're going, instead of computing the outer product between those two vectors and then multiplying with the matrix, that would cause us n-cube complexity, which we want to avoid. So what we want to do instead, we want to exploit the associativity of matrix operations to first perform the product between this matrix and vector. And once we have that, we can represent delta B as a sum of two outer products. Now, if we want to update B, we can recompute the result. But if we want to propagate delta B further down the expression, we are going to always use this factored representation as a sum of outer products, which will allow us to express delta C as a sum of four outer products. What that brings us is that we can do now delta evaluation using only n-square operations. There is no matrix-matrix multiplications anymore involved in this incremental program. So we can also support general iterative models. As you can see, with every delta propagation step, the size of this of sum of delta of outer products is actually increasing. But that's not the problem, because many practical algorithms, they often converge in very few iterations. For example, PageRank typically converge in less than 30 iterations. So how do we incrementalize general iterative models? Where we start from the state, and we have an iterative function which creates a sequence of states. And we are going to, now when the input changes, we can recompute all the states again, or we can simply do incremental evaluation. We can materialize every intermediate state. Then we can derive delta queries, and we can use them to update the intermediate state of this iterative program. So just to give you a short overview of our results, here I'm showing different use cases of complex analytics and their complexity in terms of the big O notation for re-evaluation and incremental maintenance. That is our approach. And as you can see that in all of these cases, we managed to bring down the complexity from n cubed to n squared just by using this factored representation and completely avoiding matrix operations. The only case where we cannot go below, be better than re-evaluation is when the input problem doesn't involve any matrix.
So do these business directly translate to, say, some machine learning models? Because you said
Sure.
most machine learning models are programmable on top of this.
Yes.
So can you build a model and incrementally maintain it using the same algorithm?
Yes. So this is a general model. For example, you can fit linear regression model into this, expressed as an iterative program, or any other program that you can compose using these basic matrix operations, and which doesn't involve vectors, right? Because matrix vector operation is n squared, and we cannot beat that, right? That's the lower bound. So if your input algorithm involves matrix operations, yes, you can incrementalize in this way. Okay, so how well does it perform in practice? So here we measure the performance on top of Spark for up to 100 nodes. And we measure the performance for doing the 16 power matrix operation, computing the 16 power of given matrix A. The size of A is fixed. And what we measure here is how much time it takes to process one rank update. That means, for example, changes in one row or changes in one column. And as you can see, that re-evaluation is, as you add more nodes, right, then the time it takes to re-evaluate is obviously going down, right? But it's still order of magnitude slower than our approach. And in our case, it seems like that incremental view maintenance doesn't scale, which is not true, because for incremental view maintenance, the input problem size is actually too small. And all of these numbers that you can see below are just overheads of the communication overheads from the underlying engine, Spark. Right. We also tried to fix the number of workers to 100, and then we varied the dimension size and measured how much it takes to process one update. And as you can see, the re-evaluation is actually, the cost is going exponentially, or actually quadratically. But in our case, the re-evaluation is going quadratically because it requires reshuffling of the whole matrix. In our case, we are just reshuffling vectors, right, which is a linear time operation, and we can handle much larger matrices in this case. Okay, with that, I would like to conclude. So today I presented you two systems that I worked on. And the first one is DBToaster, which is a SQL compiler that produces lightweight stream processing engines that are tailored for a given query workload. It is based on a recursive incremental view maintenance techniques. And it supports single-tuple and batch execution in both local and distributed environments. In practice, DBToaster can achieve up to 5 orders of magnitude better performance than other commercial systems. And actually, DBToaster is released. You can go to our website and you can download and play with it. The second part of this talk was focused on incremental evaluation of linear algebra programs, where the main insight is where the main problem challenge is how to contain this avalanche effect where single entry change can quickly contaminate the whole output. In order to deal with this problem, we introduced this factor delta representation, which allows us to contain the avalanche effect and achieve asymptotic improvements compared to naive evaluation. Okay, just a short about some possible future works. Right now, we have seen that sensor data are generating enormous amounts of data, right? And this data is usually shipped to the cloud storage, where it's processed by data practitioners. And soon enough, this approach won't be able to scale and won't be able to support large amounts of data that are being increasingly generated by sensors. So what we want to achieve here is we want to push the computation that is happening right now inside the cloud. We want to push it all the way to the edges of these sensor networks and perform both relational operations as well as domain-specific operations inside sensors before shipping the aggregated result or the valuable insight back to the cloud storage. Right, and the work that I've done together with Jonathan and with Rish here is one step in that direction, where we try to introduce DSP operations inside the stream processing engine. And it turns out that it can be very successful. We can leverage existing algorithms for implementing this system. Now, the challenge is how do we do similar stuff with other domains like numerical computations, approximations, statistical models, and things like that, right? So I believe this is one challenging direction that we can take. Okay, with that, I would like to thank my collaborators from EPFL, with whom I worked on these two projects, also Jonathan Grish, with whom I worked on the Trill. And yeah, I'm glad to take any questions if you have.
Coming back to the first part of your talk on the DBToaster evaluation, so you were using multi-core processing there, I presume?
No, DBToaster is just a single node.
I see. So what were the bottlenecks? Like, was it the memory bandwidth? Like, was it the random hash lookups?
Yeah.
For the kinds of queries that you were looking at?
Yeah. So it was the memory bottleneck. So we don't have a very good cache performance, mostly because it's a streaming workload, and we need to do random lookups, and it will quickly clear out our cache, right? We have to have good instruction cache locality, right? Which is very important because it's very hard to mask those kind of cache misses. But for data locality, I mean, in these streaming scenarios, we are doing our best, and our data structures are optimized for this kind of, but we'll still kind of have like 40% of cache misses, just because we just have streaming data, which is clearing out our caches.
So the numbers that you quoted were approximately at the higher end, it was around 1 million tuples per second of processing. So does that translate directly in these queries to around 1 million hash lookups that you're looking at? Or so because on a reasonably modern machine these days, you can get around 10 million hash lookups per second.
So we do have even better results than that. For some queries, I think we are going around 30 million tuples per second. Yes, that would translate into hash lookups that we're doing at least that many. And in some cases, because we have multiple trigger statements, we're doing even more, right?
So I'm guessing more joins means more hash lookups.
Well, we try to avoid hash joins. We try to avoid joins because this recursive compilation will often enough completely eliminate joins from our query processing. All we do is just summing up, iterating over some maps, and updating the result. We don't do any join processing often enough. Not in all cases. Yeah. So that's basically one idea, that with this recursive compilation, you can get rid of this classical database operators that we have.
But it's still a join, right? Because there is a map that you're looking up. So that's really what, at the core of it, a symmetric hash join is nothing but map lookups.
Yes. Yeah, and our internal implementation is in-memory hash join, right? So
in a way, what you've done is you've created a fused operator that basically fuses the join and the aggregation, and essentially kind of processes it.
But he's trying to pre-aggregate. So.
Yeah, these views are already pre-aggregated. So in many of these cases, you won't do any pre-aggregation on top of that, right? You will just do a lookup and update the result.
Do we have any more questions for Miloš? Okay, then I would like to thank our speaker.
Thank you.